Okay, this example is going to give us a couple of options here that we didn't have to deal with on that last example, which is cool. First thing you can right off the bat see is that we get to have actual data for this. We don't have to do with summary. All right, so that's awesome. So let's read through. The fun size of Snickers bar is supposed to weigh 20 grams. That's what it's supposed to be. Because the penalty for selling candy bars under their advertised weight is severe, the manufacturer collaborates the machine so the mean weight is 20.1. So extra super close, right? That's your mean weight. Means it'll be just a little above, just a little below, right? Could be, but right on. The quality control engineer at M&M Mars and Snickers manufacturer is concerned about the collaboration. He obtains a random sample of 11 candy bars, boom, weighs them, and obtains the data shown in Table 1. Should the machine be shut down and collaborated? That's the question on board. Here's the deal. Shutting down the plant is unbelievably expensive. So he decides to conduct a test with, look at this level of significance. We're not giving ourselves. This is 99% confident, right? He's got to know if he's going to shut down the plant, you got to be basically positive, right? If you don't manufacture these correctly, that you're looking at this, you're going to get a huge bill, right? So the penalty is severe. So you don't want to have a penalty and you don't want to be super expensive trying to shut this down. So we have to be confident. So do you see the difference there that we're looking at it? Cool, right? Okay. So here is 11 pieces of data that we're looking at. Now, let's swing back over here real quick. When we're looking at this sample, all right, is obtained using a simple random sampling. Nailed that. The sample has no outliers from the population, is normally distributed, or the sample size is large. Our sample size is not large. So because of that, we have to make sure that we know there are no outliers and that this is normally distributed. All right. Also, we have to make sure that the sample size is less than 5% of the population. So we're pretty confident about this part 3, right? So 11 candy bars is definitely less than 5% of all of the Snickers fun size bars that this plant is producing. So we're good there. The real question that we have to do work on is this second part. Looks like I did too much of that. This second part, and that's where this comes in. So I pulled this together for you already, and we're going to look at this here in just a second. So I already pulled this together for you just to save time. So whenever I'm determining if this is normally distributed, the first thing that I'm going to look at is on this normal probability plot here, right? I'm going to look at the correlation that goes with this. My correlation, and I just already have it calculated, so I'm going to give it to you, is 0.967. All right, that's the correlation between the weights here and these expected z-scores. So here's my score. So this is saying between two standard deviations, right, and my weights that I'm looking at with my scores here. So that's what I have. And so this correlation is right here. Now, one way to determine if this is correlated, then we come over here. There's a critical value chart. We have 11 as our sample size. So we're looking at sample size 11, and I get this critical value, and we're making that comparison. Here is 0.923. If our correlation is bigger than the critical value, then this indicates a normal plot. That indicates my data is normal, all right? Because my correlation is greater than my critical value, that indicates normal. All right, here's the other thing. Part of what we're looking at is our box plot. Are there any outliers in my box plot? No outliers that I'm looking at here. And that's the purpose of the box plot. All right, so everything is within realm, so we can now proceed with the hypothesis testing. Because this sample is small that we're looking at, then that's going to make that impact. Now my precedence, that was a bigger sample size and it was a population, right? So then we're okay with that. All right, so now we're stepping it out. The first thing we want to indicate is our hypothesis. So this is a mean, and for our mean, it tells me that our manufacturer is at 20.1. So that's where we're starting with. And what we want to know is concerned about the collaboration, obtains a sample, weighs them, and shows us data. Should the machine be shut down? Am I concerned if these are above? Am I concerned that these are below? No, I'm concerned that these aren't 20.1. Whether it's above or below, I'm getting a penalty. So I'm more concerned that this is not 20.1. I don't care if it's above or below. The machine has to be calibrated if it's off. And that's the key with this. All right? Okay, so you should have StatCrunch up so that you can be working with this at the exact same time. To save time in the video, I went ahead and already put that data in. I'm going to scoot it over. Already put that data in StatCrunch. All right, just to save time so you're not waiting on me typing that in. But we go to the same place. This is a mean, so we're going to t-stats, one sample, but now I have data, right? I'm not given the standard deviation. So when we have the summary, we have to put in standard deviation. We have to put in mean. We have to put in all that stuff. I don't have any of that. I have my data, and StatCrunch can figure out the mean and the standard deviation for me. That's nice. But I do go to my hypothesis test here. So I'm at 20.1, and I just say it's not equal to that 20.1. So then we compute, and we get our p-value. Right? So our p-value, see, there's the mean. There, oh, that's not standard deviation, that's standard error, which is something different. But it tells you what the mean is, but we don't need that because it automatically throws down our p-value for us. 0.3226. So our p-value is 0.3226. I'm going to scoop this up a little bit here. Oops, that's not helpful, is it? The p-value is equal to 0.3226. Now, if I have this scenario, right? So 0.3226 is what we have. I'm going to make that comparison. If the p-value is what? Less than alpha, we reject. All right, then we reject it. So here I'm looking at my p-value. .3226. Where is it? Oh, I'm looking all over the place. I gotta tune in. Is that less than 0.01? No, in fact, it's substantially bigger, right, than we have. So it is not less, so I'm just going to put a line through there. A lot of times in my stat lab, it'll have greater than 0.01. So if that's the case, do not reject. So what does that mean? That means our data holds true, right? So if we are not going to reject it, means what we have is valid. We're going to keep this. We're not rejecting it. We're going to keep this. Do we need to recalibrate that machine? No, we are good. So there is not sufficient evidence to conclude. I'm going to scoot this up a little bit just to make it easier to write on. that the Snickers have a mean weight different, that the Snickers have a mean weight different than 20.1 grams. The machine should not be shut down. Just, make sure we understand what is happening. Should not be shut down. No need to cost the factory that kind of money, right? And this is why we do hypothesis testing. Look at how we do this piece of data. We look at those 11 samples. We can pull those right off of the machine and we can decide, okay, are we all right? Are we still good to go? Yep, good to go. Keep up production. Keep doing what we're doing, right? All based on a little p-value. Hypothesis testing is cool, right? And super helpful. This is really good statistics we're learning.